So for our manufacturing project, we decided to do material extrusion by form of 3D printing. We decided to 3D print a pulley system. As you can see here, we have the pulley system laid out in all its components. After we designed and 3D printed the pulley system, our goal was to do some strength tests to the parts to determine what these parts could actually be used for rather than just printing.
Like all 3D prints, this begins with a CAD file. In this case, we used AutoCAD to design the part. We then saved it as an STL, or standard tessellation language file, and that's the type of file you need in order to open it in the MakerBot software. Here I went ahead and imported all of the components into the MakerBot software and laid them flat so they can be printed effectively. If they were not laid flat, it would need to create support. And then I go into the settings. I leave everything standard except for two features, which are the support, which are needed to ensure the part can support its own weight. Otherwise, the wheels would have collapsed in on themselves. And the extruder type, which is the default is the Smart Extruder. The Smart Extruder Plus is what is used in the labs in Driftmeyer. So the printer can go as low as a layer height of 0.1 millimeters, which is what we said was a limit in class, but we kept it at the default of 2 millimeters, which sped up the process at the slight cost of quality. After we go into the settings, we go ahead and save the file as a .makerbot file to print. Finally, you just go plug the flash drive into the MakerBot, and then you can just select the file from your flash drive, and it will set up all the printing automatically. It's all handled by the software.
Here's the MakerBot printing out some small parts. Always make sure to check your units because the MakerBot will always default to millimeters, so we later had to upscale some of these parts to a proper size. We also used the LulzBot to make other 3D printed parts, and we were originally going to compare the size of the parts, but due to a mismatch in scaling, we were unfortunately unable to compare the parts.
Alright, so here we have a picture of the finished goalpost Y-shaped piece. You can see it's about 3 inches long. These are the pulley shafts. Here's a close-up of a smaller piece that we made, showing that you could get pretty small, about 1/8 of an inch in diameter. And then this is the finished shaft pulleys.
So here we have the fabrication lab. This is where once you already have your design done in AutoCAD, and you have it saved to a flash drive, you can just bring it over here to this computer, hook up the flash drive, and right here we have the LulzBot software. This is where your design would appear right there. You can mess with the orientation, try to, I guess, choose the most efficient layout. And here we have the LulzBot itself. You have the spool of the material. If you have to connect a new one, you just simply feed the material into this tube up here. Then there's the machine itself, and really it just does all the printing by itself. It can take a while, but once it's done, you just come here and then pick up your part and you're done.
So here's a close-up of the pulley casing. You can see that there's a little bit of a rough surface finish, and there is that base that will need to be peeled off. This is one of the smaller connector pins. It was originally actually too small to be printed. We had to scale it up about 3 times size. You can see due to the small tolerance that the threads on the pin seem to be smudged and bunched together. Here there was a little bit of a tolerancing error between the shaft fitting into the pulley casing device. And so what we had to do is we had to do a little bit of our own machining and drill into the casing to make the hole bigger for the shaft. In order to complete this, we just used one of the provided drills and drill bits in the Fab Lab. Went ahead and clamped the 3D printed object still and fit it to size. In the Fab Lab, we also conducted a strength test on our device, and in order to do this, we found a Home Depot bucket and tied it to the pulley system, and then placed objects of known weight into the bucket and recorded the values of the weight until there was a failure. This is the scale that we used to record the object's weight. We started with several objects of about ½ pound and then worked our way up to larger objects when we saw that the part was not near failure.
Here's us starting off testing our pulley by adding weight little bit by bit. Here's us starting to add more and more weight to the bucket. As you can see, we needed a pretty significant amount of weight, and you can see on the pulley it's starting to bend whenever it zooms in a little closer. As you can see, the part is close to failure with all of the bending going on and the deformation. So as you can see here, this is the part on the pulley that broke, and the numbers in the bottom left are the weights that we put the pulley under. In conclusion, we found that 3D printing is much better for prototyping, as you probably want a little bit more weight than 38.2.